Okay, so let's start from the first student. Please. Do we have the slide? Okay, so Marcin. Yes.
Right. Good morning, everyone. So my name is Marcin Nawrocki, and today we will talk about part of the research I've done during the second year of my PhD. So I think we can all agree on the fact that DDoS attacks are a major threat to the internet infrastructure. And new vulnerabilities such as the memcached attack break new attack volume records every year. So there are several mitigation techniques, and one of them is the remotely triggered black holing. Black holing is a BGP-based mitigation technique that blocks traffic to a destination prefix. The great thing about black holing is that it drops traffic before it reaches the victim and also reduces the load for intermediate networks. However, there is an obvious drawback. Black holing filters all traffic to the victim. This means that there is no difference between malicious DDoS traffic and productive traffic. We call the dropping of productive traffic collateral damage. So this has two consequences. First, the DDoS attack becomes successful because the users cannot reach the server anymore. Second, the victim does not receive any status information about the attack because the black hole is active. And the only possibility to know if the attack is still going on is to deactivate the black hole and activate it again. So to prevent collateral damage, we need a fine-grained black holing solution. And one possible candidate for this is a BGP extension called BGP FlowSpec. BGP FlowSpec allows to drop traffic also by transport layer properties, such as protocol, port, packet size, and so on. To give you an example, in this case, the victim of the DDoS attack could drop all the malicious UDP traffic based on the memcache port. However, the HTTP request would still reach the server. So this leads us to the research questions. How large is the collateral damage introduced by black holing? Are we actually able to differentiate between the DDoS traffic and the productive traffic? And the third question is, what are effective deployment points for BGP FlowSpec? So detecting DDoS attack would be detecting DDoS traces would be the first step. However, detecting DDoS traffic in the network is quite challenging. The first problem is the limited visibility. We have to deal with packet sampling and also traces only for specific time ranges. Second thing is that sudden traffic changes are not always malicious. So, for example, flash crowds that increase the traffic volume are legitimate. So we tackle these challenges at two vantage points. So at the ISP, we use a data set that is already labeled by the MAVI anomaly detectors. And at the IXP, our second vantage point, we actually have to do labeling by ourselves. And we identify the DDoS traffic by public black holing announcements. So let's first take a look at the ISP. At the ISP, for every DDoS event, we assume, we check every DDoS event and assume a black holing mitigation technique. So to give you an example, from March 2015, we see here a TCP SYN flood. Black holing would drop over 800,000 packets. However, if we would use every property of the attack we know, we would drop around 40% of packets less. So this is the amount of packets that would be saved by FlowSpec, or that we call collateral damage. We did this for every DDoS event, for every attack type over several years. And to give you the box plotted data for 2016, you see here that we actually have a collateral damage of around 20 to 30%. We also asked ourselves, how complex do the FlowSpec rules have to be? And we did this also again separated by the DDoS type, and we counted the components that we need to separate DDoS attack from the productive traffic. What we find out is that we do not need many components. We do not need complex rules to save productive traffic. Usually, we only need 3 to 4 components. So let's compare this to the IXP. Just to recap, at the IXP, we use public black holing announcements to infer when a member IP at the IXP was under DDoS attack. We check the traffic properties before the black holing and during the black holing. We did this for half a year. What we found out is that actually around 70 member IPs were protected by black holing. We saw only 18 IP addresses DDoS traffic, and only 4 IP addresses actually had productive traffic before the DDoS. To give you an example how this looks like, so what we see here is the traffic to a specific IP address present at the IXP topology. Over time, and on the y-axis, you see the number of sampled packets. The gray background indicates the time of black holing. We learned 2 things here. First, indicated by the green circle, sampling kills small mice flows, which means that the legitimate flows were almost not visible. The second thing we've seen here is that we had only UDP attacks, at least for our cases. The good thing about the amplified UDP traffic is that the traffic from amplifiers to the victim is actually not spoofed. So what we did is we checked where are the amplifiers located in which networks. And what we found out is that around 35% of the amplified DDoS traffic actually originates from a member AS. And another 23% of the ATO traffic is only 1 AS hop away. So we argue that this locality of the ATAC traffic actually allows fast mitigation. To conclude my talk, we saw on average around 30% collateral damage introduced by black holing. We saw precise filtering of DDoS traffic with flow-spec components, and that is actually possible. Flow-spec does not need many components to save productive traffic, only around 3 to 4. And we saw fast mitigation of amplified DDoS traffic at the IXP, and that is actually possible because of the locality of the amplifiers. So, the last slide are the next steps. In the future walk, we want to have a more detailed model of legitimate and malicious traffic. And one thing FlowSpec also allows is not only the dropping of packets, but also rate limiting traffic. And we want to investigate on the benefits of rate limiting. 2 more things. There are also scrubbing centers that filter DDoS traffic, and we want to check if we actually can create more fine-grained legitimate hijacks to those scrubbing centers. And at the end, we also want to check what would be a acceptable trust and propagation model for BGP FlowSpec to be deployed. Thank you very much for listening this early morning to me.
So is there any question?
Yes. All right, so BGP FlowSpec allows the mitigation by transport layer properties, which means that if we see attacks that actually happen at layer 7, we would not be able to mitigate them with FlowSpec. So if in future the development would be more around layer 7 attacks, then it will be very difficult to handle them with flow spec. However, if they keep at the level of amplification, where we just discovered new amplification services that are that we are able to filter only on the transport layer, BGP flow spec would still be able to do that. Yeah. So the question was, how many rules can we have, right? And how I get this point. Okay, so to the first question, actually major routing suites already implemented BGP flow spec. It's standardized since 2009. And Cisco, Juniper, and so on support it. The open routing suites just caught up. I think BERT, for example, supports it from version 2.0, I think. And on the second question, actually, about how many resources they use, there was a NANOP talk at, I think, just two months ago, which has specific numbers on them. I just don't have them in mind right now.
Idea on roughly the number of rules that you could support on any kind of a router interface and what additional resources it would actually consume on the router? And also, do you know how far the IPv6 support for flow spec is?
So what we did in some of the tests was to create random BGP flow specs and enter them in a table just to see how it behaves. And what we saw is a linear growth. So we basically checked one or two of the implementations of the routing suites. But I don't have precise numbers to give you now for the memory and resource utilization.
Is there any additional question? Okay. Thank you, Martin. So the next speaker is Quentin de Koning.
So hello everyone. So it's a presentation about multipath TCP and network handovers. So what multipath TCP? It's a network layer a transport layer protocol that allows to extend TCP in such a way that you can use multiple networks at the same time. Let's say the Wi-Fi and the cellular. And so there are two main use cases for multipath TCP today. This is the bandwidth aggregation and the network resiliency under user mobility, for instance, when you have mobile devices. And we are interested in that case in particular. And about the deployment of multipath TCP, iOS is the most deployed implementation of multipath TCP. Now, any application in iOS 11 can use multipath TCP, and so we will study this case. So let's take our situation of interest. So today there are more and more voice-activated applications like Siri, like Google Now, and so on. And also users are still asking for more network content like streaming video, audio, and so on. And so they also move, the user. So let's say at the beginning you are on a Wi-Fi and listening to music and doing some Siri stuff. And you are both connected to Wi-Fi and cellular. And the question is, what will happen when you will leave the Wi-Fi reachability? So how does multipath TCP will cope with that user mobility? So with that case, actually, multipath TCP is interesting compared to TCP because with TCP, if you lose a Wi-Fi, the connection will be broken, the application will be notified. Here everything is completely hidden to the application, so the application is not aware that there was something that happened. So about iOS multipath TCP, there are three possible modes today where multipath TCP can be run. The first one is the aggregate, which is not really public, it's only for developers, so it's just aggregating the bandwidth, but mobile devices, you don't want to use all the cellular for your video if Wi-Fi is available. Then there is also another mode, which when the Wi-Fi is completely lost, you go on the cellular. And then the interactive mode, which is actually the scheduling that was used before with the Siri application, and which is now available for all applications. It tries to keep low latency. And the question is, how well does this low latency behavior works with our study. So to perform a measurement, we made an application called Multipath Tester, so it is available on the iOS store. We had more than 100 users, and it performed a lot of different kinds of tests. And one of the tests we perform is the mobile one, where we have 20 users and a little less than 200 measurements. And we perform a Multipath CP run with Multipath Quick that we presented at Connect before to see how it behaves with Quick 2. And so the traffic of interest, the actual traffic of interest is this one. So we have two connections, one for an upload traffic and another one with a download traffic. And we are doing a kind of request-response traffic where we collect the delay between sending a data and collecting the applicative acknowledgement. And so the test runs until we are completely lost the Wi-Fi, and we collect a lot of metadata like TCP info and so on. So first question is about what is an handover. What do we call an handover? So this is like a possible way of switching from Wi-Fi to cellular with Multipath CP. So after some time, the Wi-Fi is going to have a retransmission. Then for some reason, the phone will start using the cellular. But Wi-Fi cannot be lost, completely lost. It can be switching and so on. And so there can be a gray area where you are using both Wi-Fi and cellular. And so this is what we call actually the handover, and we are interested in the duration in Multipath CP of that handover. And so here is the way to be observed. The first thing is that about the abrupt handover, so just Wi-Fi and then cellular, and if I start using cellular, I never use Wi-Fi again. It's quite rare. It's only 10% of our measurements. Actually, with Multipath CP, the handovers can last more than, in the typical case, it lasts more than 10 seconds to completely switch from Wi-Fi to cellular. So the network handover, actually, it's not an abrupt process, and this is interesting because it seems multipath protocols we can do interesting stuff in that area. So then, with Multipath CP, why are we using the cellular interface? Actually, in the interactive mode, we have 4 conditions which are stated here about the round trip time, if it's go over a threshold, the RTO, if it's go over also a threshold, or if you are sending new data while you are experiencing the transmission of Wi-Fi, or the Wi-Fi assist application of Apple that does obscure things. And so when we look at our measurement, we notice that actually it's mostly because we try to send new data when we have a transmission that cause the cellular usage, but this is mostly because our traffic does this pattern. And then now, what is the latency that is perceived by the application when you have these handovers, actually? And so we compute the delay that we observe with our traffic, the maximum delay that we show, and we observe that in the median case, actually we have like 3 seconds of possible latency. So it means that if you are doing Siri, during 3 seconds, your phone will do nothing. So it's not very interactive. And you have slightly better performance in the upload case rather than download, because the sender selects the path on which you will send data, and the phone has a little better view of the network than the server. And also, we also noticed that we have a very huge latency for a few cases, and actually those are related to special configuration, network configuration, where you have an IPv6 Wi-Fi and an IPv4 only cellular, because the implementation of Multipath TCP is not complete in iOS, then you have these kind of pathological cases. And then we also decide to compare the performance of Multipath CP with Multipath Quick, and so we observe that actually we can do better than what we have Multipath CP. This is related to 2 reasons. The first one is that because of Quick, we can multiplex all the data streams over a single connection, so you can exchange data between both connections. So if you experience a loss with the upload stream, the download stream can be aware of that, since it can switch quicker. And the second thing is that it's Quick is at applicative level. You can do more complicated scheduling like applicative, deadline, and so on, which is not possible with MPTCP, which is in a kernel. And also, yeah, here it's a point comparing our test between MPTCP and MPQuick in the download case. You observe that, yeah, for a single case, you can have one or two order of magnitude of difference. In the sense that you can have tens of seconds of latency with multipass CP, like while you can have like 1 second with multipass quick. So to conclude, multipass CP it's a seamless handover at transport layer in the sense that the application will not notice anything. So, but while still trying to send on the Wi-Fi because cellular is expensive and so on. But yeah, the issue is that with interactive applications, today multipass CP, the way it's implemented, the way the scaling is done, it's maybe not the best for this kind of application. And so we are going to study more with multipass quick, especially because it's more flexible, and maybe we can find a better trade-off between the cellular usage and the latency that we experience at the application. Thank you.
If you have any question, please.
Yeah, so it is a multipass TCP in the iOS kernel. So this is not the Linux one, which is the most studied. So actually, iOS in MPTCP is not. I don't think there is any study about iOS in MPTCP because it's quite new, and because Apple never made any publication about that. And multipass quick, it's an implementation that we presented at Connext. And it's a quick go, so a G-Quick, where we added an extension so that you can use multiple paths. Actually, yes, because the multipass CP is in the kernel, and the kernel is open source. Yeah, but you have to dig in. Yeah, it's completely separated, and actually it's not the same implementation, and unlike the Linux implementation, it does not implement fully multipass CP. Like it missed the add address feature, and this caused the issue that I just mentioned with IPv6 and IPv4 stuff. Yeah, the handover and the aggregate. So the handover, the difference is that I think it's even more conservative in the sense that it will wait that Wi-Fi is completely lost, while here the main use case of the interactive is to have low latency, so it uses cellular a little more aggressively. But it still keeps the user preference of Wi-Fi over cellular. While aggregate, it's just a bandwidth aggregation. But we cannot experience at large scale the aggregate mode because it's only for phones that have iOS beta. And so if you want to have a full question, we tried, and actually it crashed the phone on which a production phone. So we stopped using the aggregate mode.
So what's your biggest takeaway with regards to the design of multipass?
Sorry?
What's your biggest takeaway with regards to what we need to change on multipass TCP?
I think there is something to change in the scheduling. Typically, the scheduling has to be improved, to be more clever. The issue with multipass TCP is that the scheduling is only the kernel, and the kernel has to remain simple. You cannot keep a lot of memory and a lot of complicated heuristic inside the kernel. So one possible way to improve multipass TCP, at least for the iOS case, is to offer a way to define the scheduling at user space. So in some place, like with using a function on the node.
Thank you, Quentin. So our next speaker is Pedro Marcos.
So good morning, everyone, and thank you, Marco, for the introduction. I would like to start my presentation with a little bit of context about what is happening on the internet today. So what we have seen in the last years is that network operators are relying even more on IXPs to improve their traffic delivery performance on the internet. And the main reason for that is because IXPs are offering a rich path diversity. They are interconnecting hundreds of ASs and offering reachability to thousands of prefixes. But to benefit from this rich connectivity of IXPs, there is a problem that is before exchanging traffic, the operators needs first to agree to start exchanging traffic. And the process of interconnecting as of today is mostly manual and length and driven by personal relationships and brand image. So just to illustrate, the process starts with finding a potential peering partner. This can be done by checking your personal contacts or going to an Euro IX meeting. Then you find a peering partner, you go there and discuss the properties of the interconnection, you formalize the terms, and then finally you deploy the agreement. And this entire process, according to some operators that we have talked, it takes like a few days or a few weeks to be concluded. So there is a really limited responsiveness to the internet traffic dynamics. So as a result of this process, operators miss interconnection opportunities. They have inefficient utilization of their peering ports. We can observe a lot of spare capacity at the IXP ports, and also the traffic delivery is not optimized. So here's an example. Let's focus on ASA. ASA is sending traffic towards ASC and D, and then a traffic surge starts and it starts degrading the performance of the traffic, including the traffic surge towards C, but it also degrades the traffic towards D because the path is the same, at least the first hop of the path is the same. So, but if we note A could reach D towards the XP, but there is a problem here is that A does not have an interconnection agreement established with 2 or 3, and it takes time to establish this interconnection agreement, so it cannot mitigate the impacts of the traffic surge. So to unleash this unexplored potential that IXPs have to improve wider traffic delivery performance, we have some requirements. The first one is to replace the manual process to something more structured. We also need to provide to network operators an expressive interface in which the operators can express what they are offering, what are their peering policies. To replace the personal relationships and brand image, we need a way to allow them to build trust instead of to automate also the process of building trust. And we need to do all this process in a privacy-aware manner because operators are very concerned about exposing information about their peering policies or the terms of their interconnection agreements. So we propose here Dynamics. Dynamics is a framework that allows operators to improve wide area traffic delivery performance by quickly exploring the rich connectivity opportunities at the IXPs. Here is an overview of how Dynamics was designed. Dynamics is a daemon that every AS that is connected to the IXP and wants to benefit from these features that we are offering needs to run. So it's a distributed approach. We decided to do it in a distributed way to facilitate the process of achieving the privacy of the peering policies, since the peering policies are locally stored at each AS, so it's not available for anyone else except if the AS wants to make that information available for the others. And also to keep the IXPs neutral in the process. We have spoken with some IXPs operators and they said they are not quite interested in interfering in the business relationships of the ASs that are connected there because all of the ASs are their clients. So Dynamics has 4 components. The first component is a protocol that eases the process of finding other peering partners and establish the interconnection agreements. We also have an interconnection intent abstraction in which the operators express their peering policies, what are they offering and what they want. We have a distributed ledger where the ASs can find information about the other ASs related to past previous agreements. So instead of only rely on personal relationships, I can check the past performance of the other AS based, for example, on feedback of the other operators and take my decision. And we will also have a component, we call it a legal framework, that it intends to provide some guarantees about the properties of the agreements. So in case of there is a dispute, there is a template with the properties of the agreements stored there, and then the ASs can handle the dispute. We already did a preliminary evaluation of our solution. To evaluate dynamics, we have coded it in Python, and we are using Hyperledger Fabric as the ledger to store the information about the previous interconnection agreements. We ran some experiments on AWS, and our first question that we have tried to answer here was the benefit of our solution. So if it takes time to explore the rich connectivity of XP, with Dynamics, how long does it take to establish an interconnection agreement? Remember that today, this time is between some days or weeks to be completed, according to the network operators. So here is an example of the experiment that we did. Since there is no prior history about how the ASs will behave establishing the interconnection agreements, the idea was to do a scalability test. So from some number of ASs, all the ASs on the experiment are trying to establish an interconnection agreement with the same AS. It's a throughput test, it's a stress test. So we measured 2 times there are 2 different times that we have measured. In this plot, the y-axis represents the average time of our experiment, and the x-axis is the number of ASs that we run the experiment. So the blue line represents the time to find an interconnection offer in this throughput test. In the worst case, it's around 80 seconds. And the time to effectively establish the interconnection agreement with 200 ASs trying to do the same thing at the same time is around 2 minutes. And if we compare this with the current process that it takes some days or weeks to be completed, we are achieving our primary goal of enabling the use of the rich connectivity of the IXPs. So if we transform that number in the number of agreements that an AS can establish per minute, is around 80 agreements within a minute. We are aware that this is not practical on the internet. There is going to be a lot of routing instability problems, but this is just to show the throughput that we can achieve. We are studying how to mitigate the potential impacts of dynamics on the routing stability. But just as a comment, in regular conditions where there is no stress test, a pair of ASs can establish an interconnection agreement in less than 10 seconds, which is quite good. So in summary, we have presented an approach to unleash the potential of IXPs to improve wider traffic delivery performance. And more important than that, we are doing this preserving the privacy of their peering policies, which is a concern for the network operators. So with Dynamics, we are going to enhance the responsiveness of the internet traffic dynamics, be able to increase the peering policy utilization, and also create new economic opportunities for the AS, because since they are able to interconnect much more faster, maybe they are going to be able to establish new agreements that they wouldn't be able to establish in the current situation. Currently, we are evaluating the impacts of Dynamics in terms of storage requirements, since we have to store information about the previous interconnection agreement. So how does it will cost for the AS to have this information? And also the bandwidth requirements, because Dynamics is designed to run over the IXP infrastructure, so we are not willing to interfere on the traffic that is running on the IXP. And finally, currently, we are partnering with a company that offers a global peering infrastructure to deploy Dynamics and offer it to their clients. So with that, I conclude my talk, and I'm more than happy to take your questions.
Yes.
Danke. Well, after speaking with network operators, their main concern is that they have their peering policies, for example, who I'm going to interconnect, or what are the routes that I'm offering for the other ASs when I establish an interconnection agreement, and also what are the properties of my interconnection agreements that I have established. So I believe that we are achieving this by keeping all this information about the peering policies locally stored on the autonomous systems, and the AS will only disclose that information if he's intended to establish an interconnection agreement with someone. So if someone tries to interconnect, asks for an interconnection with that AS and he's not willing to interconnect, he can simply ignore the request and not disclose their peering policies.
So what information are you planning to store in the ledger? Because that seems to be about reputation and past connectivity, which seems to contradict the privacy aspect.
Yeah, that's a good question. We are also working on this aspect. We didn't define yet the exact type of information that we are storing on the ledger. It can be more like a feedback by the operator saying, oh, this was a good AS to interconnect, so there is no private information here. But it can also be more related to adherence to SLAs or control plane information. But there is a problem here that I'm aware that we need to guarantee that no information that is related to the business policy would be available for the other ASs. Well, trust is, in our case, is just a way to complement the information that the ASs have to decide whether or not to interconnect with another network. So our idea is to provide a set of information. It can be like subjective information or control plane information or data plane information about the previous agreements, and let the own AS decide how to use that information to decide whether or not they should trust the other network. I repeat. Well, we have been observing on the internet some events like traffic surges and network outages, so we don't need to be in the order of seconds, but we definitely need to be better than we have today. For example, today we have seen case of outage that lasts for 12 hours a day, and maybe then the ISP is not able to deliver the traffic accordingly, but if there is something like Dynamics, he could reroute the traffic to the ISP and handle the situation. So that's our main motivation. And also, we are in our ongoing work, we have some IXP trace data analysis where we show that there is a lot of spare capacity at the IXP port, so we also think that this capacity could be better utilized since they are paying for having that capacity.
So which additional steps are necessary besides signing the contract to actually have traffic flowing, and what's the time that it takes to do those?
Well, the time to, I'm assuming that you are mentioning the time to deploy the interconnection agreement after they establish the agreement. So the time to deploy this is currently not part of our design, and this is based on information from the network operators that they told us that they already have scripts to automate this process, so it's more like just an engineering process and not a research challenge. So we can add this on Dynamics, but it's not part of the research itself. Well, according to our IXP guy that works with us and has the experience, it don't take that long. It's some minutes, I think.
Okay. So thank you very much, Pedro. I would like to invite on stage now Mohamed Al-Asmar.
Good morning, everyone. I'm going to present Polyraptor, which is an efficient data transport protocol in data centers. So before starting talking about Polyraptor, I'm going to talk about the challenges that we are trying to tackle in this research. So we have 4 main challenges here. The first one, we are trying to have an efficient one-to-many data transport protocol in data centers, where we need to create replicating copies of our data to different servers, like in Google file systems. And the second challenge is we are trying to have a reliable many-to-one transmissions where a client can fetch data from different servers, like in distributed storage systems. And the third challenge that we are trying to tackle here is we are trying to eliminate incast. Incast happens when there are multiple concurrent senders sent to the same receiver. That's going to create a bottleneck at the receiver's link, and that's going to make throughput collapse to all senders. The fourth challenge here, we are trying to have better utilization of data center by using per packet transmissions instead of per flow ECMP. So we are proposing Polyraptor, which supports one-to-many and many-to-one reliable transmissions, and it eliminates incast and it supports multipath, as we will see now. So I'm going to start talking about the design of Polyraptor. That is here, as you can see, we have one sender and one receiver. So Polyraptor is based on fountain codes, mainly Raptor Q codes. Just to give you an idea about the beauty of fountain codes in this scenario here, imagine you have a glass that you want to fill that glass with water, and you have a fountain. You don't care what are the drops that you are going to use to fill that glass. So as a receiver, I don't care what are the symbols that I'm going to receive from the senders. They all are equally useful for me. So that's the main feature of Raptor Q and fountain code, mainly fountain codes and mainly Raptor Q. But that doesn't stand alone. So we have a receiver-driven approach. So the receiver, which is me in that case, I'm going to control that fountain, and I'm going to get as much as I want number of symbols based on the connection, as we will see here. So what we do here, so we have one sender and we have one receiver. So we divide the data into source blocks. Then for each source block, we encode our source block into what we call encoding symbols. So each encoding symbols include source symbols, which is the original source block, plus repair or redundant symbols. So the first feature here is Raptor Q codes are systematic codes. That means we have in our encoding symbols the source data that we have here. What's the beauty of this feature? If there is no condition in the network and there are no losses, if we receive the whole source symbols, that means at the receiver side, we don't need to do decoding. So that's gonna make it better performance. The other feature here, we don't care about ordering here. So what we do here, we just spray buckets. So that if there is a loss, that's absolutely fine. We don't need to have any kind of acknowledgement or retransmissions, these kind of notions that we have with TCP. Because the receiver is going to request another one, and the sender can provide us with limitless number of repair symbols. So this encoding block can create endless number of encoding symbols based on the requests from the receiver. So the receiver is going to request another one, we will receive another one. Now the receiver has received 8 symbols, which is K in our example here. That's just an example. And the receiver now can start decoding. So for the receiver to be able to start decoding, the receiver should receive minimum K number of source symbol, which makes sense. Otherwise, if you receive less than K, you can't decode the whole source block. So after receiving K, the receiver is gonna start decoding, and it doesn't matter what order we receive, and it doesn't matter if we receive source or repair symbols. They all are useful for the receiver. So ordering is not important here, and they are rateless codes. You can get endless supply, no need for retransmissions. The last feature here about decoding. Decoding, Raptor Q has an excellent decoding performance. I'll give you numbers here. If the overhead is 2 symbols, so for one source block, if you just receive K plus 2, the probability of failure will be 10 to the power minus 6. So this implementation is based on the user's requirements. So if the user wants to start decoding immediately after receiving K number of symbols, the probability of failure will be 10 to the power minus 5. If the receiver is going to wait until, if the receiver is going to request 2 more, K plus 2, the probability of failure will be 10 to the power minus 6. If you will get more, the probability will go low. So again, in fountain coding, any subset of encoding symbols are useful. It doesn't matter what is received or lost. the only thing that matters here is to receive enough number of symbols. So it's a receiver-driven approach. The receiver is the one who's going to control that fountain, which is the sender. So by using RaptorQ, we can target all of our challenges, as we will see now. So in the first challenge, in many-to-one scenarios, we have here 2 senders and 1 receiver. So the sender, both senders, we have the same data at each sender, and the client, which is the receiver, is going to fetch data from these replicas here. So we need to make sure that each sender is going to create a unique source encoding symbols. Because if each sender is going to send the same thing, that doesn't make sense, because we are going to create replicas in the network without any usage. So we use different seeds for each encoding block at each sender. So each sender is going to create unique encoding symbols. Then after we are employing NDB switch, so we have 2 queues at each switch, data queue and header queue. So after receiving a data from one sender, we add a pull request at the pull queue at the receiver. So at the receiver side, upon receiving data packet, the receiver is going to add a pull request for that sender. So we received one data packet from sender 1, we add pull request for sender 1. We received another one from sender 2, we add pull request for sender 2. Now the receiver is going to start passing requests to each sender, and the receiver knows the capability of its link, because in data centers we know the bandwidth of our links. So the receiver is going to pass based on the link speed to make sure that it's not going to create congestion at the receiver side. That's why we eliminate encast by this way, because if you use TCP, if the packet is going to be dropped, you have to wait for timeout. The receiver won't know about what's happening in that switch. But in that way, we have a fast, so for example, I'll show you this example now. So if that shallow buffer queue, the data queue is full, if an incoming packet to that switch, we don't drop that packet, we trim it, and we take the header to the header queue, which is a priority queue. So that's kind of fast notification to the receiver about what's happening there. So upon receiving either header or data queue, the receiver is going to add a pull request for that sender. The other feature here, if one of the senders can't contribute to this transmission as the other one, that's absolutely fine. So if if the link of sender 1 is congested, that's fine. We keep requesting from sender 2, and at the end, as you can see here, we have received 4 symbols, 4 from sender 2 and just 3 from sender 1. That's absolutely fine, because they all are useful for us. So this is many-to-one. Sorry, I need to skip that slide. I should have removed it. That's mainly the NDB paper, which was the best paper in SIGCOMM last year. Okay, so in our simulation for many-to-one, we use 250 servers, and we simulate 10,000 sessions. Each session has a size of 4 megabytes, and we run background traffic of 2,000 sessions, and we simulate traffic matrix permutation and random, and we have 2 scenarios of 1 and 3 replicas. So for the results of many-to-one, here we have what we call session. So the session here means we have 3 senders and 1 receiver. That's 1 session. TCP doesn't support many-to-one communication. That's why we use like multi-unicasting TCP connections, as you can see here. So in our results here, the black line, the black dashed line, as you can see, it's just for 1 sender based on Polyraptor, and the red dashed line is with the 3 senders based on Polyraptor. The x-axis represents the rank of all the sessions that we run, and the y-axis represents the good port for each session. So we run 10,000 sessions. Each session has a group of 3 senders and 1 receiver. We do the same thing for one-to-many. So in one-to-many, we have 1 sender and 2 receivers here, as you can see. So we have pull queue at each receiver to request packets. So the sender is going to send 1 packet. We don't create replicas at the sender side. We make the switches to create replicas, because we don't want to create congestion in the network. So after receiving replica from the switch, the receiver is going to add pull request. then add pull request, then it's gonna start pacing the request. After receiving another request, it's gonna send another data packet to the receiver. And the results of one-to-many, again, we have here one sender and 3 receivers. It's kind of multicasting groups here. We have 10,000 again. And the results here, the y-axis represents the good port. And as you can see, Polyraptor achieves better performance than TCP. Finally, these are the results of incast scenario. We are running 70 parallel servers who are communicating to the same receiver. And as you can see, there is a throughput collapse when we run TCP, and we achieve better throughput with Polyraptor. So to conclude, by using Polyraptor, which is based on fountain coding, along with NDB switch, along with receiver-driven approach, we are able to achieve all of our goals by having a reliable many-to-one, one-to-many, and eliminating incast, and using multipath by spraying a bucket instead of using per flow ECMP. Thank you. That's the probability of the failure in decoding. Yeah. You fail to decode. Yeah. Yeah. If you receive more, that's gonna be low. Yeah. There is a graph, I don't have it here to be honest, but as far as I remember the number, it's gonna be either 4 or 5. Yeah, I have a graph that shows all these things. Yeah. Yeah. I can't hear you, sorry. Yeah. So as I understand, you are saying, why do I compare my Polyraptor protocol with TCP? Yeah, yeah. Okay, I think the main contribution here is employing fountain codes, because fountain codes has a lot of features that we can benefit from them. But fountain code, as I said, that can't stand alone. So we need another mechanisms for congestion control and flow control mechanisms. So I think the answer is there is nothing can stand alone. We need all these features to come together to get all the goals that we are trying to achieve in this research. Yes, please. Yeah, okay, so the current work, I'm not going to call it disadvantage, but the current work that we're trying to work on now, we are trying to implement these in real-life systems and to see what are the latency, what are the complexity that we are trying to have here. Fountain Raptor Q codes, they are linear. The complexity of them, it's linear, which means the complexity equal big O of 1. So it doesn't matter what size of encoding symbols you will have. So the K value doesn't matter what K value you have here. Yeah, as I said, it's because it's like linear, the complexity is linear here. So we have like a feeling that's a promising thing from the current results that we have here. They are promising, and yeah, so in simulations, we didn't see any problem in the delay that we have here. the next step, which is the current work that we will be working on, implementing this protocol on real systems.
But problems, what if the sender just want to send like two small packets? And what if that kind of condition happens, then you require sending expanded to very long series in order to make your coding works? Then you have a very low utilization of the entire
So
bandwidth.
if you have small packets that you want to send here, that means, so the maths behind the encoding block there, it's just simply multiplications of matrices at the sender side. At the receiver side, it's just a Gaussian elimination process. So if you have small packets, you can just have a small matrix, and the time there won't be any delay there because the matrix is going to be small. That means that's going to be fast and that's going to work fine.
Waste of a lot of bandwidth, is it?
I'm sorry, I think I'll have to cut it here because we are going out of time, but Mohammed also has a poster downstairs, so you can continue also offline.
Right,
thank you very much, Mohammed. So our next speaker is Patrick Kalmbach. So please come on stage.
So hello everyone, my name is Patrick Kalmbach and I'm from TU Munich. So I started my PhD last year, and what I'm presenting here today is more like still work in progress, so it's not like a final project and we're still working on it. And shortly to my bio, so I did my master in computer science with background more in artificial intelligence, and what I did there was looking a lot into how you can make sense of data. And when I came to networking, I saw that we have here a lot of graphs, so graphical representation of data. We have, for example, router level graphs, we have S level graphs. We can represent the World Wide Web as a graph. We can represent IP-to-IP communication as a graph. And those graphs are not really easy to understand, and they will grow even more complex if you think about the IoT. This will add a large number of additional nodes, for example, to our IP communication. And we still somehow have to manage those massive networks. We have to make somehow sense out of it. And if you, for example, get a graph like this, well, if you have a smart layout program, like the program with which I generated this visualization, and you have a certain hypothesis about your graph, you might already see, for example, well, okay, here I have, for example, my stars. This is what I expect. I might want to expect a certain structure in the core, for example, but yeah, so how to really see those patterns and how to expect patterns that you have not thought about beforehand. So patterns that might be new, patterns you simply don't have in mind. And if you have then a representation like this, you immediately see, for example, hey, okay, cool, I have functional groups here. I can directly put usages to those groups, and I can understand what's going on in that graph. And those two graphs are really the same. And if you have something like this, for your communication, you might use this, for example, to generate access control lists or identify abnormal behavior that does not comply to this pattern that you see here. You can actually understand and see what's going on, so you can really project those thousands of nodes down to maybe only a couple of tens, which you can then really look at and understand what's going on. And you might then use this also for traffic engineering or resource allocation. The question that I started to look at then was, okay, how can I go from this hairball graph, from this unstructured data to more structured visualization and representation? And what we looked at a lot during my studies was probabilistic generative models, which are really a great tool to infer or model from data. And in this setting, you represent your data as a probability distribution. In this case, I use a probability distribution over graphs, which is parametric, and those parameters then encode the structure of your graph. So they encode what's going on. And the nice thing about this is now that you can give this process, you can take the data that you have, infer those parameters, and then you can also generate synthetic data back. So this you can, for example, then easily use for simulation purposes. and one model that we learned about, for example, was the stochastic block model, which was designed in the back in the 80s. And this model has two assumptions. The first one is your graph consists of k groups that interact with each other, and edges form only based on the group membership of incident nodes. So basically, given the group membership of two nodes, I can tell you whether there is an edge or not. What can you do with such a model? So you can really represent, it's very flexible, you can represent a large amount of different communication patterns. For example, you can represent assortative mixing with this, which you can see in peer-to-peer networks. You can represent assortative mixing patterns, or you can represent ordered mixing patterns, and you can also represent combinations of those patterns and even more ones. And that's what you can what you can also then infer back from your data to make those visualizations. And why would you want to use such a graphical model? So the first thing is it has interpretable parameters. So you can actually make sense out of it. You can interpret them, you can look at them, which is, for example, different if you just take a neural network or just take a clustering algorithm which outputs something, but it's not really clear how this interrelates. You can easily compare different hypotheses by looking at, for example, likelihood or other information measures. You can easily generate synthetic data for simulation, or for validation. You can estimate missing or future structures, or you can identify structures that shouldn't be there. And it's scalable, so to create a model, you don't necessarily need to look at all nodes. A representative subset might be enough. And what we now did a little bit was, on the one hand, look into security. So we used this model to infer basically the structure of IP to IP communication in a university network. And then we found, for example, nodes that do stuff like this. And it turned out that those were bots, and we were able to find those bots very reliably. What we also started to look at is unrolling this model over time. And here, for example, can identify also structural anomalies. So in this case, there was something happening in that red circled time step. We don't know yet what exactly it was, but yeah, something strange was going on there. So what happened there? Another thing that we looked at is the synthetic data generation. And here you can, for example, also include a categorical distribution over your groups. And this allows you to also scale the graphs, the number of nodes in the graphs. What you do then is simply draw the groups for the nodes, and then draw edges according to those group labels. And this gives you then a synthetic graph which has the same large-scale organizational structure as the original graph, but the connections might be different, and you might look at different, okay, what happens if my hosts communicate in a slightly different way or communicate to different servers, so you can maybe also then analyze that a bit. And what we presented here in a poster session was then the inclusion of weights, of edge weights, and this would then also allow you to not only create a large-scale communicational structure, but also, for example, the size of flows that are running between those nodes, which you might then use, for example, for validation, or maybe also for other machine learning purposes if you're lacking the traces or the data to actually do this well. So in summary, what we did so far, is extract this logical structure of communication networks. We mostly did really looked into it and reflected the structure. Does it make sense? Does it comply with intuitions we have about this network? And we did some proof of concept work, for example, regenerating traffic using this weighted stochastic block model and checking if this actually matches or improves what we can obtain with alternative models. And we also looked a little bit into how we can do anomaly detection with this. And for the future work, what we want to tackle next is basically incorporate node metadata, that you can, for example, have better groups that align better with metadata and improve your intuition about what's actually going on, and also to obtain good prior distributions for unseen nodes. So basically, given the node metadata, you can then derive a probability distribution over the groups. So basically, at the moment, if you don't know the group membership, you're a little bit lost. So, and with this metadata, you can then fit those nodes to respective groups. And then we also want really to investigate how we can use this for network management, for example, use this to predict the sizes of flows, and then use this to make routing decisions, use it for structural anomaly detection, so change point detections, or use it for behavioral anomaly detection, basically detecting malware. So that's it from my side. Thank you for your attention. If you have any questions, I'm happy to answer them. Hmm. This is basically the probability of edges between nodes then. So this is a little bit a chicken egg problem. So you can derive the model from your data, but now assume you have one new node which you don't know the group membership of. So which group does it belong to? You have not observed, for example, edges yet. It's a new node that comes to your network. You don't know edges yet, so you can't really fit it into that. And at the moment, you can't say which group this host might belong to. You can use the categorical distribution and say, okay, I have here very large groups, so it's most likely one of those. But if you have additional node metadata and incorporate it into your model, you can condition this on a... This you can do, yes. Yes, you can do, yeah. Okay. So the stochastic log model actually originates in the social sciences. It was heavily developed now in the last 10 years in a statistical physics community, complex system theory. And you have, I don't know what you are referring to. So are you referring to modularity? No, this is basically the methodology from that domain.
Okay. So let's thank again, Patrick. So this is our last presentation for today. So Suraj Jog. Okay, perfect. Thanks. Let's start.
Good morning, everyone. I'm Suraj Jog, and today I'll present my work on enabling dense spatial reuse for millimeter wave networks. So currently, the Wi-Fi bands that we operate on have very limited bandwidth, and these cannot enable throughput-intensive applications like wireless VR or wireless 4K video streaming. So to alleviate this problem to some extent, the FCC recently released up to 14 gigahertz of unlicensed spectrum in the millimeter wave band. So with such huge amounts of spectrum available, you can now have wireless links that give you data rates of something like 4 Gbps, and this can enable exciting new applications. However, these millimeter wave radios are actually quite different from the traditional radios we have today because they use very directional narrow beams to communicate with each other. And this means that now we have an opportunity to enable extreme spatial reuse because we can add multiple APs side by side and they can all communicate simultaneously without interfering or having to timeshare the channel. Now, this is something we don't traditionally see in wireless networks today because the antennas are omnidirectional. You place multiple antennas side by side, they still interfere and they time share the channel. Of course, there are many advanced techniques like distributed MIMO and so on, but these typically work only on the downlink and the associated complexity in the system is higher. So given this opportunity for spatial reuse and the fact that now you have multi-Gbps wireless links, millimeter wave is now a very good candidate for exciting new applications like wireless VR for education or wireless VR for professional training, where you might have military personnel who are training for combat situations. And over here, you require dedicated high bandwidth links to each user in the network. Another very exciting application this enables is robotic factory automation, where multiple robots have to stream high quality video back to control servers to help them take decisions and collaborate and accomplish tasks. Now, one thing to notice here is that we're talking about networks with multiple users. If we had just one student or one soldier, it's not that hard a task because we know millimeter wave can give you the required data rate. But what if you had 5 students, 10 students, 20 students? Can you still enable that each of them can get the data rate they require to enable such an application? So our objective in this work is, can we design a real-time and a practical protocol that can achieve this vision of spatial reuse and enable multiple links to communicate at such high data rates? In order to achieve this vision, we need to address 2 key challenges. One, how do you align the beams of the radios in 3D space? And 2, how do you accommodate for client mobility and the dynamic nature of the environment? So let us look at the first challenge. As we said, millimeter wave is directional communication, and before you can start transmitting packets, the beams need to align towards each other. Now in a network with a single link, this is pretty straightforward, right? You align along the line of sight path. In fact, even in a network with one AP and multiple clients, you want the AP to align along the line of sight for each of the clients. But what about a network with multiple APs and multiple clients? Is line of sight alignment still the smartest thing to do? That's the question we need to ask. So consider a situation like this, and from here, it should be evident that no, line of sight alignment for everyone is not the best thing always. Because over here, the 2 links involved interfere, and now they have to time share the channel, which cuts your throughput in half. Unfortunately, this is what the 802.11ad standard does today. It aligns all the links along the line of sight path, and if they interfere, tough luck, you need to share the channel. But what if we could find alternate propagation paths? So for instance, over here, perhaps there might have been a metal cabinet along the wall, and you could reflect or you could bounce the signal off this metal cabinet and sustain communication for link 2 while reducing interference at link 1. So by enabling something like this, you can have more and more links communicate simultaneously, and something like this would perform better than what the naive thing that the standard does. And this is the core idea upon which we build our system Millinet. It starts off by finding all the propagation paths between the links in the network. It identifies what set of paths could coexist, and then it aligns the beams of the links either along the direct path or along some reflected path. So for instance, in this situation that we had here, Millinet would do something like this, where it would compute a set of beam alignments where link 1 would get to communicate on the direct path for some amount of time, and link 2 would get to communicate on the direct path on some other amount of time. This is done to maintain some notion of fairness because every link wants to transmit on its highest data rate path for some amount of time. What is happening on top of that is additional links are kind of squeezing in themselves within the time slots by choosing some alternate propagation paths to fit themselves into the time slots. The next challenge that we need to address is, fine, you have this idea that you can use propagation paths alternate, you can squeeze in as many as you can, but we are dealing with a dynamic environment. How do you accommodate for client mobility and the fact that things are always changing? So over here, we have these clients. If the clients are constantly moving around, then the propagation paths are changing, the interference patterns are changing. If you had to remeasure all of this again and again to compute the optimal alignment, that would require order n square such measurements for a network with n links. This is an overhead that simply does not scale. So instead, what we design is, we design an algorithm which does not require any explicit packet measurements to identify this multipath or the interference. Our key idea is, hey, why don't we reuse measurements that were taken during the beam alignment phase? So to step back a bit, as we mentioned, communication is directional, so the AP and the client have to align the beams together. The way this happens is, the client is in the omnidirectional mode, and the AP sends packets in each direction one by one. After this, the AP asks the client, hey, what direction did you hear me best on? Instead, what we are proposing, the AP should ask, tell me all the directions you heard me from. So what's happening now is the standard is collecting all these measurements and throwing away most of them and choosing only the high SNR paths. We are saying don't do that. These packet measurements have very useful information, and by running computations on them, you can identify all the propagation paths between every AP and every client in the network. And moreover, by accounting for beam pattern imperfections, you can also identify the amount of interference between any two links communicating along any propagation path. So in this way, without adding any additional packet measurement overhead, our system can continuously maintain an up-to-date view of the network and can constantly self-configure and readapt itself to give you the best performance. And the beam alignment happens once every 100 milliseconds. So it's constantly getting updated information about what's happening in the environment. So building upon these two key ideas, we implement our system in an experimental test bed. Here are the 60 gigahertz radios that we use, and this is the room layout where we set up our experiments. The blue squares represent the AP positions, and the green locations are where the clients are distributed. As preliminary results, we wanted to understand how the total network data rate changes with the number of clients. We run two kinds of experiments where, in one case, the antennas are equipped with 3-degree wide beams and the other with 12-degree wide beams. Now, as you can notice here, Millinet scales the total network data rate with the number of clients. This means every additional AP that you add, you get proportional gain in the network data rate, which is not true for the standard. As you can see, the network data rate saturates very fast. And there are two reasons why we have such gains over the standard. One, the standard only uses fixed line-of-sight paths, and it has no expressibility in squeezing in more links in between time slots, which is something that Millinet can do. And two, Millinet has a very efficient way of measuring all the interference in the network. In fact, it can do it within one beam alignment phase. What the standard does today is actually very naive. It schedules explicit packet transmission slots where it exchanges packets and measures the interference. And it does this in a pairwise manner. So with n number of links, you have to have order n square such packet transmissions. And that's a huge amount of time to collect the interference information. And as a result, it also takes way longer to converge to the optimal beam alignment. In fact, over here, we can see that Millinet can deliver data rates of more than 38 Gbps for 10 clients, which is almost 6 times higher than what the standard could achieve. And this is about 3.8 Gbps for each client. So this really gives us some hope that our system is along the right direction to achieve this goal of spatial reuse and give each user the amount of data rate required for high bandwidth applications. So something like 3.8 Gbps is actually sufficient to enable wireless VR for the applications we mentioned in the beginning. There is some body of related work. Some of them is for wireless data centers. In fact, in SIGCOMM 2010 and SIGCOMM 2009, there were similar ideas of bouncing signals off the ceiling. But those are more for static topologies, and the interference patterns are not really changing. Our problem is a little more challenging because we need to deal with mobile environments. There's been some millimeter wave work too, but it's either for static links or, for instance, in some cases, they augment the environment with various sensors to help with the alignment and so on. Yes, thank you. Yes, yes, please. Yeah. Yes. So one thing is we assume the orientation is fixed. So given a fixed orientation, you just need to scan all your possible directions. So oh, I see, I see. Well, it is linear in the number of directions too. You're right, you're right. But we are not taking that into account because that does not change with the number of links. We are mainly looking at the dependence of the measurements on the number of links in the network. And given the question about number of APs and number of clients, for now, we've always assumed that the number of clients and number of APs are the same. If there's a mismatch though, we have mechanisms to deal with that too. Yeah, please. Yes. So it's not as many as well because, so I could see that you were talking about maybe multiple reflections. The signal energy actually attenuates quite a lot after one single reflection. So second order reflections are still observable, but third order reflections are not as much. In fact, millimeter wave is also known for having sort of sparse reflections. So on average, we see about 3 to 4 paths. And the way we identify the paths is during the beam alignment, the client captures all the packets of the AP it heard. So if it heard 4 packets, it knows there were 4 directions. And the AP marks each of these packets so that the client has some perspective that from the AP side, what the orientation was. I hope that answers your question. Yes. Yes, yes. Um, so with multicast, the beams are actually quite narrow. You would have to have something wider. And so another approach is, why don't you have like multi-pronged beams? Like you have like 2 beams and you direct them towards 2 clients. That's a little harder because if you were to do that, you need explicit control on each of your antenna elements. That requires multiple digital chains and it is not as easy. Yeah, so it requires more hardware sophistication, which is not envisioned to come into the current customer level hardware. Thank you.
Okay, so if there are no more questions, then I would give a round of applause for Suraja. And I would give also another round of applause for all the candidates. So so they knew only yesterday evening that they had to present this morning at 7 a.m. So you can imagine the stress and the amount of work that they put. The presentations were really great. So thanks again. And especially thanks to all the jurors also for coming here in a massive number at 7 a.m. This was very, very nice and appreciated. Thanks a lot. So just one information. So we will announce the winners at the closing session today. So thanks a lot.